Okay, and the last thing which I would like to mention here is about the support of our new model, which is traveling wave electro-optic phase modulator. So just to give you a bit more details, a bit more explanation on the module itself, I would like to jump directly to the idea first for the model. So to represent correctly in the simulation the traveling wave electrode or traveling wave modulator, we need to mainly correctly account for the different voltage values at the different stages of the electrode. To be able to mainly account for this matching or mismatching between between the electrical and optical signal, we need to make sure that we segment our electrode in multiple sections. And you can see that each of the section in our case is represented by the waveguide modulator. It will have given length, and what we will be doing, we will be really calculating the reflection of our electrical and optical signal at each stage, and we will be calculating the effective voltage which is being applied to our optical signal at each step of the segmentation. So how it's being represented in the simulation directly, you can see that here we have the model which directly reproduces the S parameters for each section, and we have single waveguide modulator, which is defined to the number of sections. So based on this, for each segment, we will have a single S matrix and a single of waveguide modulator being applied, and the signal will just overlap over each other. And what is quite critical here, you can see that in this case, in this design, we are directly applying the ground signal ground configuration. So we have two modulator signals, two modulators, while signal is being passed between them. So we are just inverting one modulator on the other side. And from the idea of the theory, we are accounting here also for the electrical impedance mismatch, for the signal reflections at each facet, or I mean at each step of the simulation, and also about the velocity mismatch between the optical wave and microwave, mainly allowing us to calculate also the electro-optic effect here. And based on this model, we have created additional, we created like this compound model, this compact simulation model, which is referring the parameters exactly to this value which I explained, so allowing us mainly to set the electrode length by the number of segments and the segment length, enabling us to just load some measured S parameters, define the load and source impedance, and also to define the effective and group indexes of our optical and electrical mode. And with that, I would like to just refer to one of the demonstrations, which is describing this model in more detail. So we have the 2 terabit data center interconnect with optical frequency comp based on the film theme lithium niobate modulator. And I will just run the simulation already before I will jump into a bit more details. And especially I would like to show you the modulator design, which is complete IQ modulator with our design of our traveling wave lithium niobate Mach-Zehnder structure here. So as I showed, this was just modulator, so we need to really build Mach-Zehnder with adding additional waveguides and MMI connections, and by cascading 2 of them, one for I and one for Q, you can see complete the design of the modulator. So what we should focus in this demo is firstly that at the input we are creating the optical frequency comp, which is just our input for our modulator, and we are also generating the IQ signal, the QAM signal, the electrical QAM signal here based on this model, which is just a driver IQ to drive the electrically our signal. Then we are adding additional logical information, because logical information is not carried completely in samples, so we need to mainly make sure to restore it to get proper information about the phase change and the bit sequence. We are passing it via fiber and going to the typical DSP set of DSPs to recover correctly the phase and make some downsampling to our bit error estimation model. And here we are then coming back for the visualization of the spectrum. And just I would like to show you now the results, which are just appearing on the other screen. And what we can see here is firstly our optical information, our optical spectrum of the frequency comb, our launch signal, the received signal when we are just observing only single channel, and in just few seconds the complete constellation diagram will appear. And here you can see that we have constellation diagram for 32 QAM with additional estimation of the symbol error rate depending on the index of the channel we are providing.